And then I think I'll start from here. Good afternoon, everyone, or good morning, depending on where you are. Thank you for being here. We hope everyone is healthy and will stay that way for this crazy and unconventional times, to say the least. Make sure maybe your microphone is on mute. I think it sounds like it is, at least. I hope the sound quality is good and you can hear us well. This is a time to make small adjustments before we start. And through this event, feel free to write your questions. There is a Q&A interface there where you can, write your questions, and we'll do our best to go through all of them. We will try to have 2 Q&A sessions. Q&A 1, which will be in about half hour when we see the first setup on converging optics, and then a final Q&A at the end. And we'll also conduct a small poll also at the end, which it would be very nice if everyone could participate in the poll. The organizers of this webinar are Guillaume Chief Technical Officer of Imagine Optic, based in Orsay, France. At one point, Guillaume will take over, and we'll see him live in the lab, or more like a conference room in France. Jerome Balesta and myself, Philippe Clemenceau, we are both based in the US. Some of you know us already, I'm sure. Jerome is based in Sacramento. I am based in Boston. And we're here to show you a live demonstration of our new R-FLEX 2 system for optical characterization. This is a first webinar out of a series of 3. The next one will be on wavefront measurement and adaptive optics in a few weeks. And in this demo, we will show you 2 examples of setups. The first setup will look at a camera lens, and the second setup would be on a zero power component with a collimated beam. Okay. But please, even though we're showing this simple characterization, keep in mind that the system can be used for many other optical systems to be characterized, which could be much more complex. So here in this slide, actually, I'm showing, very simple components, dichroics, wave plates, lenses, mirrors. But of course, it could be a combination of lenses, like an objective. It could be a VR system. It could be a large telescope. It could be even a full optical bench setup that you have in your lab, passing through all the lenses and characterizing the wavefront and so on. This is how we'll spend our time for the next hour. Hopefully, we won't spend too much time on the slides, maybe just 10 minutes. We'll do a quick introduction, and then we'll go to the live demo. Setup 1, as I said, an objective characterization using the R-FLEX system. And we'll spend some time on the wavefront sensor as well. And then we'll stop and do a Q&A on setup 1. And then we'll move to setup 2, which is a large diameter setup with a 100 millimeter collimated beam. And then we'll just look at a parallel glass. And then we'll have a Q&A as well at the end of setup 2, and then some closing remarks. So just to tell you who we are, actually, Axiom Optics is actually the US subsidiary of Imagine Optic. We started in 2010, and we also offer a full diversity of optical instrumentation. So, not just wavefront sensors, of course, but also, microscopy systems, A lot of customers here for the cameras, also for in-gas cameras, high-speed cameras, or scientific cameras, intensified. We also offer beam profiling systems, even for high-power lasers. In optical metrology, so we do, of course, the R-FLEX systems, but we also offer a 3D light field camera. We offer adaptive optic solutions and also positioning hexapods. We have people in the West and the East, 3 people in California, 3 people here in Boston, and we have lab space here as well. And then, of course, you know, the type of customers that we have here, it's kind of a representative, but, you know, universities, R&D, labs, you know, large companies, industrial companies who do quality control and so on. I think this is quite representative. And then I'll leave here Guillaume to start on this. Guillaume, are you connecting right now?
Yes, I am. I hope everybody can hear me. Thanks a lot, Philippe, for this kind of introduction. Let me just present in few words Imaging Optics. So our main knowledge is wavefront sensing based on Shack-Hartmann technology. So we have a very large product range of wavefront sensors adapted to many wavelengths, many resolution, many accuracy. Of course, if we are able to measure the wavefront, it's always interesting to correct it. So we have in-house 2 technologies to manufacture deformable mirrors. The first one is for high-power laser application. It's based on mechanical actuators, and these kind of deformable mirrors are available up to 500 millimeters diameter. And we have also a small one. It's a deformable mirror dedicated for bioimaging, let's say microscopy or ophthalmology. All these kind of deformable mirrors can have up to 100 actuators, basically. Of course, in order to drive the wavefront sensors and the deformable mirrors, we need software. So we have a software dedicated to metrology, which is WaveView, and another software, WaveTune, dedicated to adaptive optics. We do also systems, engineering, and services. Today, I will present a system. Its name is R-FLEX 2. It's an optical metrology tool that is dedicated to optics characterization and more precisely transmitted wavefront of these optics. It's based on a wavefront measurement and a Shack-Hartmann wavefront sensor. What is interesting in this device is that it's a self-illuminated wavefront sensor, which means that it integrates a light source. It is basically made to measure transmitted wavefront of any kind of convergent optical system. What I mean by convergent optical system means that positive focal length. So it includes camera lenses, telescopes, microscope objectives, collimators, whatever, of any kind of diameter and F number. This device is compatible with 4 different wavefront sensors. The broadband, the first fast and preliminary, a high resolution wavefront sensor. And what is interesting in this device is that it's compatible with a very large range of wavelengths, because we can use this device between 400 nanometers to 1100 nanometers. We have also another product which is called R-FLEX SWIR, dedicated to SWIR measurement from 900 to 1600 nanometers. Of course, on this device, we use in-gas camera and again, the Shack-Hartmann sensor based on in-gas camera. This device is, of course, compatible with our WaveView, which is our main metrology software, which include PSF and MTF. Let's focus a bit on the sensor we use today on this demo. It's a HASO 4 broadband. As I said, it's a Shack-Hartmann. Here are some specifications. I want to focus on 2 of them. The first one is that it is calibrated in the range 350 to 1100 nanometers. and the absolute accuracy we ensure is lambda over 100 root mean square. Those two specifications are very important because absolute measurement means that this wavefront sensor is able to measure an incoming wavefront and measures its aberration with an ensured accuracy, whatever is the aberration. For instance, if you want to measure beam which has 1 micrometer of coma, the sensor will give you 1 micrometer of coma in the measurement with the accuracy of lambda over 100 root mean square. It does not need any calibration or optical paths dedicated to calibrate itself. It is calibrated in-house. If we look now of what I'll show you on the first setup, here it is. So as you see here, we can see what's inside the R-FLEX. So we have a source. In fact, it's not a source because it's we use a source which is a laser diode which is fibered. And what you see at the top of this drawing is a FC APC connector dedicated to plug a fiber. So we create a small collimator, it is reflected by a beam splitter, and then is focused by a module, what we call a module. Here we'll use a 31mm focal length module in order to create a diverging beam. And this device, the R-FLEX 2 plus this module, is set at the focal plane of the lens we want to characterize. Here you see that we have a rod and stock objective with a focal length of 150mm and f number of 5.6. Of course, if we want the light to come back to the sensor, we need a autocollimation flat mirror. So the light is sent back to the sensor and the measurement of the aberration possible. On this demo, we'll show, of course, transmitted wavefront measurement of this lens. Zenica will see a dichromatism. I have here two sources. The first one is at 658 and the other one at 520. So we'll be able to switch from a wavelength to another to measure the chromatism of this lens. And thanks to WaveView software, we'll be able to see the point spread function and the modulation transfer function of this objective. And then I'll take the R-FLEX 2, remove from the first setup and install it on the second setup, which is a large aperture platform. As you see here, the beam now is enlarged by a series of two flat mirrors and a big lens. So now the beam is 100mm diameter. And again, it is reflected by a flat mirror. And if you put, of course, an optical filter, an optical window, whatever, with a larger diameter, we're able to see the influence of this component on the wavefront and characterize the element. The common technology that is inside those two systems is a Shack-Hartmann wavefront sensor. So this is basically how it works. Shack-Hartmann sensor is an association of a detector, let's say a CCD or a CMOS camera, whatever. We remove all the lenses and replace the lens by a micro lenses array, which is at about 2.5mm from the CCD or CMOS. And if you imagine a flat wavefront coming to this device, the micro lenses array will create an array of spots on the CCD. And if all the spots are on a regular grid, it means that the wavefront is flat because all the spots are exactly at the center of each microlens. And at the bottom, of course, if the wavefront is not flat, it creates some very small angle in front of each microlens, so the spot is shifted. And by detecting the position of all the spots, we are able to calculate the small angle created by the wavefront aberration. And by knowing the angle of the wavefront, it's in fact its derivatives, it's possible by a 2D integration to retrieve the wavefront itself. So let's switch now, I think, to the video and the demo. You'll probably see me in a few seconds now. Yes, here am I. Hi everyone. So I'm sitting here just behind the setup I just described. So this is the R-FLEX here. And we can see here as a wavefront sensor. There are two cables starting from this device. The first one is a simple USB cable that goes to the PC, and the second one is a fiber. And this fiber is connected to a laser diode here, which is on the table. You can't see it. As you see here, there is a module here. You'll see that for the second setup, I have to unscrew it to change to another module. This module here has a focal length of 31 mm, and it creates a focusing spot that is just here at the focal plane of this lens. And this lens is a rod and stock objective, as I said. And the flat mirror is here. So the beam starts from here. There is a mirror, a flat mirror here, the lens, the beam splitter, which is here, and the beam is sent here to the flat mirror and come back here to the wavefront sensor. Okay, so now let's have a look on the software. I think Patrick will be able to switch to the software. Thank you very much, Patrick. So here is the software. I can stop here by pushing this button, the acquisition live, and restart it. I have some few parameters already calculated, but I want to start by showing you the camera signal, which is here, and then increase its size in order to see something for you. So here are probably more than 3,000 points created by all the macro lenses. I can just do a zoom here on some few spots to show you how the spots are sampled by the pixels. As you see here, the pixels sample the spot by about 5 or 6 pixels in diameter, and it allows us to calculate the centroid very precisely. And as we know the spot position very precisely, it allows us to calculate the wavefront with a very good precision, very good accuracy. So here is the raw signal. Let's hide this to go to the first information we have is the centroid. It can be displayed like this. Here it's not very visible, so I can zoom here to show you. Maybe, yes, it is more visible this way. I don't know if it's, yes, okay, it's a zoom on a quarter of the device. So here the grid corresponds to the macro lenses, and here we have small vectors starting from the center of the macro lens and ending at the actually calculated spot position. So as you see here, as the vectors are not zero, it means that we have some aberration here because the spots are calculated not exactly the center of each macro lens. As you see also, if I don't know if it's possible to unzoom and see something, yes, you can also see that the aberration we're measuring here is quite symmetrical in rotation, as all the vectors are starting from the center and going at the outside of this pupil. So these are roughly displayed the wavefront derivatives. We can integrate this by 2D integration to retrieve the wavefront. And here is the wavefront calculated live. As you see, it is updated, I don't know, every 1 second roughly here in this demo. So this is a wavefront. So one thing which is important on Shack-Hartmann system is that giving the camera signal, we can get the slopes and then calculate the wavefront. It is also possible to retrieve the intensity of the beam. And here you have live, intensity, and phase. So amplitude and phase. So in one single image, we're able to measure the electrical field of light. And this feature is very interesting because for laser application, for instance, it's quite interesting to measure intensity and phase and to know how the laser will focus by just propagating using Frandsen propagator, for instance. But here we are doing metrology, so the important information we'll use here is the wavefront. Maybe some of you are experts of wavefront measurement, so maybe some of you may here recognize that this aberration contains mainly, let's say, spherical aberration. We can see a bit of astigmatism and maybe a small coma here that is visible because this center is not perfectly symmetrical here. One thing that I want to show you here is that, as Philip said, we're not in an optical lab here. It's a simply wooden table. We are in a meeting room. So if I hit the table here, the measurement is still feasible. That means that we don't need a very stabilized optical table as interferometry needs. It's not interferometry, definitely. It's Shack-Hartmann wavefront measurement, which means that the vibration can be huge. Even with the vibration, it's possible to do the measurement. This is an important thing to know. Let's come back to this wavefront. A way to analyze more precisely what kind of aberration has this wavefront, it's possible to calculate the Zenica coefficient on this. Let's do this. I will just change the parameter in the software to change to model calculation. And here I can open the window displaying the Zenica coefficient. Here it is. As you see here, we have all the first, I think, 34 Zenica coefficients, starting from curvature, which is the blue here, and we have astigmatism here, 0 degree, 45 degrees, the comma x, comma y, the spherical aberration, and then we go to the fifth order and the spherical aberration of the fifth order. As I said, the main aberration, which is measured here in live on this demo, is the spherical aberration. The amount of aberration here that is calculated by the software is 86 nanometers. I think the magnifier appears on another screen. Here it is, thank you. So it's 86 nanometer root mean square of aberration. Okay, 87 now, because it's live, it changes a little bit. Okay, let's see. Now, I have a way on my demo to change a bit the focus. What can we observe if I change just a screw to change the focus? Maybe if you have a look here, I don't know if you see the mouse, but here, as you see, the focus term increase. So I can just adjust live the autocollimation by retrieving the zero focus precisely to get no curvature on my wavefront. This is an example of what can be done, because here we have a lens, so I can't change the aberration of this lens. But if you have, for instance, a telescope or a collimator based on two mirrors, and you want to align this telescope, it's very simple to, for instance, see that the comma can disappear if you align one mirror compared to each other. So you have in direct, in live, the information of comma that can be decreased by touching one mirror to align perfectly the telescope at the end, and then get the final characterization of the telescope after it is aligned. So it's not only a tool for doing characterization. This tool can be used also to align the optical system, more generally. So after we have seen this aberration here, what we can do is calculate diagnostics. For instance, we can calculate the bond spread function. Oh no, before that, I want to show you something which is important. Here, what we see on the software is the wavefront of the objective. It's what I want to see. But a question could be, okay, but what about the aberration coming from the device itself? I have mirrors, I have a beam splitter here, I have a lens here. So maybe all these have some aberration. How can I remove this from the measurement? It's quite easy, because, in fact, before in order to prepare this demo, I created a reference here, which is here. That means that the measurement here that is displayed is not the raw measurement coming from the wavefront sensor, but the raw measurement minus a previous saved measurement that has been done on a concave spherical mirror. Let me explain this. This is a small concave mirror. I don't know if you can see this. It's a very small one. So if now I have a way to put this mirror at the center of curvature, the center curvature of this mirror, exactly at the focal plane of this lens, I'm able to save a measurement and then save all the aberrations that are coming from this device. So now, if this concave mirror is a perfect sphere, and this flat mirror here that is behind the lens is a perfectly flat mirror, what is displayed here is only the aberration coming from the objective. And this kind of stuff here are available in our accessories, but I'm quite sure that all of you have already seen this kind of stuff in your optics lab. Flat mirror and concave mirror. It's very simple. And then the only thing that we have to take care on how we set up the software is that, as I said, the lens is crossed by the light 2 times. The beam passes through here and is back. So we measure twice the aberration of this objective. In order to display only the aberration of this lens, we just have to click here double pass. There is an option in our software. Double pass, please divide all the aberrations that are measured by 2 in order to display only the aberration of the objective. So first calibrate the thing using a concave mirror, use a flat mirror, and then divide by 2, and you have live the aberration coming from this lens. Okay, let's now try to see what can we do with this aberration. First, I can try to calculate the point spread function. Here it is. The point spread function can be calculated directly from the information of the phase. It's just a Fourier transform of the field at the end. So it's possible to calculate here the point spread function. And I have a slider here. I can change exactly the plane where the calculation is done. So I can do a through focus calculation of the point spread function. I can see that the best focus is around here. And for instance, now I have a point spread function. I can calculate the modulation transfer function, which is calculated in 2D. And again, I have here a slider allowing me to change the focus in order to check that I'm exactly at the best focus in terms of MTF. As you see, the MTF here is changing depending on the focus I want to analyze. Let's go here. What is interesting here is that I can have this information live. If I run the software here, we have this information updated at the frequency of the activation of the system, which is here about 1 Hertz. So I can again optimize an optical system, not based on the wavefront, but based on the point spread function if needed, or based even on the MTF. I didn't show you that, but you can extract from the 2D MTF the profile you want, and even do an average of all the profile in order to get an idea of the MTF, whatever is the orientation of this measurement. Okay, this is done for that. Now what I can do, as you see here, the wavefront will show a lot of aberration at the edge of the pupil here. So maybe if I remove from this objective a ring corresponding to the very edge of the pupil, I'll be able to optimize the quality of this lens. Let me do that. This objective has an iris, so I can I wrote this in the slide, but here the lens is has a f number of 5.6. Let me just close the iris a little bit. Let's go to 8, and then here I have a focus stem that I can remove it. As you see here, the aberration is now 31, 32 nanometers. So this lens is very better in terms of aberration if we just close it a little bit with a f number of 8, although having a complete aperture of 5.6. Let me go back to 8 now, to 5.6, sorry. Here it is. So I'm back to the first measurement I did with the fully open iris, so F number 5.6. I just push this now, okay. And see what happened if I change the wavelengths. Let's again have a look on this focus. I will just try to optimize a little bit the focus in order to put this focus at exactly 0. Okay. This is now perfectly 0. Again, here I'm using a laser diode at 658 nanometers. I have just here another diode at 520. So let me just stop the acquisition. Here I have a pass-through, so I can just remove here the red and switch to the green. Okay, let's see what happened. But before starting the acquisition, I have to change something in my configuration. As I said, I calibrate the aberration of my device using the concave spherical mirror. But I did this at 658. Now I am at 520 in the green. So I need to change the reference and just update the configuration in order to load a file that has been saved on the concave mirror in the green. So here is the file. It is here. Okay. And then restart the measurement. Okay. As you see, maybe all the aberration here, as you see here, the aberration did not change, which means that roughly by a change of wavelengths between 500 and 650, this aberration remains the same, which is expected. But what is not expected at all is the curvature term here, the focus term, Z3. It's minus 0.7 micron, which means that by changing the wavelengths, the curvature suddenly changed a lot. And as I calibrated this with a concave mirror at both wavelengths, I'm sure that the chromatism is linked to the objective, which is here. So here, by doing this experiment, I'm able to perfectly characterize the longitudinal chromatism of this lens. And as you see, it's quite big, because if I display the curvature on the wavefront, it is now more than 600. I have to wait a little bit because it does not update, but here, okay, yes, thank you. The wavefront has now 0.7 nanometer root mean square error, so it's lambda, which is a big aberration. So this lens is quite good for one wavelength. But if you have a white source, a white object to image with this, for sure there will be some chromatism in your image. Well, I think this is it for this first setup. Maybe we can go to the question and answer session. Can you please, Jérôme or Philippe, just have a look on this question? I'll be pleased to answer to it.
Sure. So I have a first question. You modified the size of the aperture with the iris of the lens. Somebody asked about the slopes on the edges of the pupil that seem to be larger, bigger than the average slopes. And this person was wondering what was going on.
Okay, so let me redo this maybe. So I will just change the configuration here in order to have a look on the slopes only. Here are the slopes. And if I just try, yeah, okay, here it is. You mean that some slopes here at the very edge are a bit higher? Maybe, yes. It's probably due to diffraction, because as the iris is not perfectly in the exit pupil of this lens, it creates small diffraction, and the local slope of the wavefront at the very edge of the pupil are changed due to the diffraction of the iris. It's maybe this. It's a good question. But as you see, compared to the slopes we can see in the center of the pupil, at the edge we can see maybe some of them that are a bit higher, but it's not very clear.
Yeah, but even before, sorry, this is Philippe, even before you close the iris, you can see a ring of very red vectors. I think that was more the question.
Yes, but these vectors here are linked to the spherical aberration, which is very strong at the edge.
Exactly. So this is real signal.
Yeah.
That was signal.
From the spherical aberration, which creates very large slopes at the very edge of the pupil,
which, of course, decrease when you close the iris.
Sorry. If I close the iris, of course, this is reduced because we have no more measurement on the very edge of this lens. So the spherical aberration may disappear completely.
Mm.
Do you have typical values for the aberrations brought by the adaptation module that you attach to the R-FLEX? And how can that optical performance affect the measurement?
Okay, this is again a very interesting question. Of course, as I said, all this stuff here has some aberration. The modules especially are optimized in order not to have a lot of aberration, and all this has been specified quite tightly. I think, depending on the F number of these modules, the aberration at the output of this is between 30 nanometers to 100 nanometers root mean square. What I can do here maybe is I try, maybe let's go this way. I will just open, can you transfer just open the file, the reference file, just to see the aberration, because it's an interesting question. I just opened the measurement I done, let's say at 658 here, and see what's this. And let's see the aberration. Here it is. So this is the measurement done on the concave spherical mirror. So this is quite all this aberration and this module, which is crossed 2 times. And the aberration here on the whole rectangle is 112 nanometers. So if we extract from this information only the center, it will be of course smaller, in the range of 40 or 50 nanometers root mean square. And I'm very confident on saying that this aberration does not affect the measurement of this lens here, because it is included in the reference, and again it is subtracted. Maybe nobody knows, but a few people knows, but even piezo interferometers have quite a large amount of aberration on the output beam. The aberration we measured on a piezo interferometer had more than 1 lambda of aberration, because the technique of piezo interferometry does not need a perfect beam, because the fringes are created between the reference plane and the secondary wave. And that's the same here. Even if we have a small aberration at the output of the R-FLEX, it is subtracted by the reference.
Is there a way to survey the position of the focal point of the pattern or the tracker? In other words, is there a way to implement in front of the modules? This one I will answer. Slope diagram. Could you please so that's an interesting question. In the slope diagram, could you is it possible that you show the spot tracker working and how the tracking algorithm can follow the evolution of a spot even when that spot is going to a neighbor under a neighbor landslet?
I can do this by just, okay, sorry. I can, yes, it's an interesting point. I can do this here. Let me zoom on a few spots here. Okay, it's a zoom of one single spot, just to check that I will change the tilt in order to remove, oh, sorry. In order just to check that the tilt I'm doing is small enough. Okay, let's remove this, it's not important. Here, this is, can you please, Patrick, just send me this small window in my screen? Thank you very much. This is a tilt that is measured by the Wavefront sensor. And I can change on my experiment by changing the position of the R-FLEX. I can, or maybe I do something differently. I have the auto-correction flat mirror here, so I can change a little bit the orientation. Let me just add this and change. Yes, it is. As you see, the X tilt is changing. As you see, the spot is moving. I can change the tilt. And another spot is coming. And now, this is another spot coming from another micro lens, coming exactly the same place that it was before. And the tilt is measured correctly. This tilt minus 36 milliradian. It's because I added a lot of tilt. But the spot tracker, the spot tracker managed to follow the spots during the tilt. And this is why we are able to measure absolute tilt, whatever is the position of the spot on the CCD, even if it comes from the micro lens, which is not in front of the given area on the CCD.
Can you please the same movement with the slopes, showing the slopes and the spot on the viewer, please?
Here, this in live.
Yeah.
Okay, but the problem is that if I want to display the tilt, the vectors now are huge.
Yeah.
Because the tilt is very strong compared to the aberration. So let me just display the X tilt and reduce the vector length in order to see something, and redo the zoom in order to get only a quarter of the Wavefront sensor. Let's see what happened now. Oh, sorry. Here it is. And redo the same with my screw here. I can change the position, the orientation of the auto-collimation flat. Let's go the other way. As you see, the vectors are increasing. Okay, now they superimpose, so it's not very visible. But I can go the other way. As you see here, I have no tilt. And then I can go and see I have to unzoom here in order to follow and to see the vector's length. Oh, sorry for that, it's a bit too strong now. Here. And I can continue, go to up to 66 milliradian. As you see, the vectors are still increasing in length. And I can go even further. And see a 60 milliradian, I have still another spot coming, and the measured tilt is still okay. We're following the spots during the acquisition. Okay?
There is other question, but I think we should maybe go ahead with the second part of the demo in order to contain everything in 1 hour. I don't know what you guys think.
Okay, I'm okay. Let's switch to the other demo. Okay, let's switch to the other demo now. Yes, you're right, John. Thank you.
Well, you switch, maybe you can answer one question. What about the you were explaining how little impact the wavefront error of the adaptation module could have on the measurement, but somebody is asking about the temperature and how temperature could affect some temperature variation could affect the aberration introduced by the module, and so have some discrepancy in the reference.
Yes, of course, as all optics in temperature affect the aberrations and probably the focus term, firstly. Our advice, of course, is to have always in hand this kind of concave mirror I described in order to reduce calibration from time to time. Optics lab are usually stabilized at the level of plus or minus 1 degree C. And we know that with this level of temperature stabilization, no need of reference is the new reference, a reference acquired at 20 is still okay for 21 degrees C. But of course, if we want to be very sure that everything is okay, whatever is the temperature, you can redo each time this small reference measurement to be sure that the temperature does not affect the measurement you're doing. But that's the same for all technology in wavefront sensing. Okay, let's switch to the second setup now. I think it's time. So what I'll do, maybe Patrick can show you very quickly the large aperture platform, which is just nearing here. So what I'll do is just take this R-FLEX here and unscrew one single screw I have here at the bottom in order to take it and put it on the large aperture platform. But to question a few seconds. Okay, the screw is now removed. Okay, it's good. It's an opportunity for me to just to show you maybe more precisely the system. So we can we can see now the wavefront sensor here, the fiber. So it's a APC connector to plug the fiber, and the module in front of the R-FLEX, which is here. So as I said in introduction, this large aperture platform has been designed in order to be used with another module. So I will just show you how I change the module. So I will just unscrew the F31 module and change it to the F50 module. F60, it's a 60 millimeter focal length module. So just remove this and screw the new one. And we have quite a smart mechanical engineers here in Imagine Optics, so they design a very nice interface to set the R-FLEX on the large aperture platform. We have two very big magnets here, and this piece here is made of steel. So, and there is 3 points and 3 balls here. So I can just put the sensor, the R-FLEX, onto the platform very precisely, in order just to put all this exactly at the correct position here and here. Yeah, it is correct now. As you see, this system allows you to replace the R-FLEX exactly at the same position. Okay. As you see also, it's a question of minutes. I just changed the setup. I was measuring converging lenses, and now I'm ready to do measurement on flat glass. Zero power, let's say, zero power transmitted glass. So maybe you remember the slide describing this. So we have now the R-FLEX, always here a focusing spot, and we have 2 mirrors here. One is here, one is here, and we have big lens here. So So the beam now at the output is collimated with a diameter of more than 100 millimeters, and it is reflected by another flat mirror and set back in the system to be measured by the wavefront sensor, which is here. Okay, as I change the module, as I change the configuration, I have to do some adjustment in the software. And of course, this reference here I used for the previous setup is not good anymore. So I will just remove the reference. Now I will display the absolute wavefront acquired by this sensor here. So let's see what, here it is. This is absolute wavefront measured in light. Here. What's interesting here is that, as you see, we have a small tilt here, minus 10 milliradian, which means that the flat mirror is not perfectly in autocollimation, so I can just change a bit the orientation of this mirror to retrieve the autocollimation. For those of you who already use FISO interferometer, it's the same. You reduce the number of fringes by changing the tilt. This is exactly the same. You can retrieve the autocollimation very precisely here by looking at the measured tilt on the wavefront sensor. So here is the aberration. Now, what I want to show you. Here we deal with quite a long optical path, so it's maybe 2 meters, large diameter. So the air turbulence becomes a limitation of the measurement. And this is an important thing to discuss, is that we can very easily remove the influence of air by averaging. So what I'll do now is change a little bit the configuration of the software in order to average the measurements. So here, as you see, the measurement is not average. Can you please type 0, Patrick, please? Thank you. By putting 10 here, it means that now the system will acquire 10 images, and after 10 images are acquired, the wavefront calculation is done on the image. And this stabilizes a lot the measurement. What I can do also is use the auto-reference mode. It's a very interesting mode because automatically, when I click here, the system will save a reference and display all the other measurements done, subtracted from this first reference, automatically acquired. When I click here, this measurement is done, and now this is the difference. And as you see, here, maybe Patrick, you can send me this magnifier on the main screen, please, thank you. This is the root mean square wavefront error of sensitivity we have here in this environment, which is quite a poor environment. Again, we are on modern table here. So this device allows having nanometer sensitivity measurement on the wavefront without any very complex optical table stabilized in vibration. It's possible to do this on modern table. It's important. I can show you something here. Now, I just create heat on my hand and put my hand here at the bottom of the beam, which has 100 millimeter diameter. As you see now, as the heat changes a bit the reflection index of air, we are able to see the influence of air turbulences in the room very easily. At the nanometers level of metrology, it's very easy to see the influence of air. I will just, in order to have a faster refresh rate, can you just type 1, please? Thank you. Yes, it's a bit quicker now, frame rate. Now, let's see what happens if I put my finger in the beam. Okay, as you see, without any configuration, let's say something like mask or thing like this, the software automatically detects that there is no spot here in the camera signal, and as there is no spot, the wavefront can't be calculated. But everywhere else, wavefront is calculated. And what we can see is a bit the heat of my finger here. As you see, we can even see the air turbulences created by my finger. Okay. we have live measurement here. I can do even something even more impressive. Just it's a bomb of dry air. What's interesting is this dry air. It's cold. So what happens if I put this in the beam? Here is the tube, and I can just try to see this. Try to send the as a refresh rate is not very nice. Yeah. Okay. Ah, yes, we can see some. The problem is that I have to. Yeah, we can see some very quite interesting thing here. Okay, it's a way, but of course this is a demo, so this is not very interesting. Just to show you how sensitive is this device. I have here 3 different kinds of samples. The first one is a piece of windshield. It's quite a specific one, but it's a windshield. So what happened here if I put this windshield between the system and the flat mirror? So here you can see the effect of this windshield. The aberration is now more than 1 micron per meter square, so it's very easy. Here I just move a bit the windshield in order to see another part of this device. And it's very easy now to characterize it, see if the wavefront that is acquired is okay comparing to the specification of this glass, and analyze things. Don't forget that by knowing the wavefront, it's very easy to calculate the local curvature of the wavefront and calculate the diopters, which is closer to all the rules and normalization of all this kind of device, windshield and glass. Okay. Here is another sample. You should recognize that. I can also try to see what happened. As you see, you can see things here in transmitted wavefront. So again, it's possible to analyze plastic things in order to see where are the injection point, for instance, if the specification of this kind of device are reached. And last sample is a piece of glass. It's a floated glass, so it's very interesting to see because, as you see, it has a very particular structure. Only one direction. Here is vertical thing. If I rotate now the sample by 90 degrees, you see now, of course, this is vertical. So this is coming from the fact that this glass is floated. So it's basically made by very hot glass, which is spread on tin, and this creates this waves here. So it's very important for this guy to know what kind of thickness, inhomogeneity are in this kind of lens, this kind of glass, to check that this glass can be used for other purpose than just a window. As you've seen, we did many measurements here. We still here 3 nanometers per meter square wavefront error. And we can do many kinds of things by doing this. I want to conclude this demo by showing you something interesting now, again. And this will be my last thing. As you probably already saw here in this device, there is a Shack-Hartmann wavefront sensor, and I can very quickly remove only the wavefront sensor from the R-FLEX tube and use this wavefront sensor as a wavefront sensor, for instance, to measure laser, to measure something else. And if I want to re-put this sensor on here, the bench, thanks to this very smart mechanical interface, I just re-put this and retrieve the same measurement that I had, 3 nanometers per meter square. So here we started from a converging optics to flat with no power glass, And we ended by the possibility of removing the sensor in order to do other measurements. So it shows how what the huge number of applications of this kind of device. Philippe, don't you want to conclude maybe this way?
Right. So what we'll do right now, I just have one more slide of conclusion, and then there are quite a few questions, and we can do that, in the next minute, basically. All right. So let me see. Let me share my screen now. And so just to summarize this, and then we'll do a final Q&A. Huh? So please stay put. We've showed measurements in this webinar on flat and converging optics. We actually showed that we could do some alignment with the system, because we can get a few measurements per second. And we can see, the influence of lens positions and, on the coma, for example, on spherical aberrations and so on. And we can do some characterization. So, meaning like, measuring MTF, measuring Wavefront, measuring the Zenica polynomials, measuring the point spread function, and also we showed a measurement of chromatic aberration. We showed quite a nice accuracy, I think, especially in these conditions. The accuracy of the system is lambda over 300, the repeatability of the system. And also, despite the environment, we showed that, even with some vibrations or on a table, which is not an optics table, we could get these kinds of accuracy. Now, I think that I hope everyone appreciates the modularity of the system, the fact that it's multi-wavelength, and the ease of use, meaning that we can take out things. We can take out the R-FLEX from the large aperture collimator. We can take out the wavefront sensor from the R-FLEX, position them again, and we get consistent results. We can change the optical fiber and do the same thing with a different wavelength. Referencing was shown when we were making a reference on the flat mirror, for example. We didn't show it on the spherical mirror because it means that we had to, attach it and, maybe align it and so on. And also, the insensitivity of the system and how it behaves with masking. So when Guillaume was putting his finger in the screen, he didn't just disturb the whole measurement. You just keep getting measurements where the finger is not there. And that's, some other systems don't have that kind of behavior. And then again, we showed some relatively simple examples today, a flat piece of glass and, a camera lens, but this applies to other things that could be much more complicated with many more lenses and many more interfaces, or things that are bigger, like telescopes, a biomedical instrument, for example. A whole microscope can be characterized this way as well, or any kind of benchtop optical setups that you have. And to finish here, Jérôme, you can, these are the equipment and the specifications that kind of summarize the system here. There's two R-FLEX, one for 400 to 1100, actually it's 350 to 1100 nanometers. Different resolutions can be chosen because you can use different sensors, different focusing modules, so you can adapt the numerical aperture, and different collimators from 25 to 150, maybe 200 millimeter. We can do things on request, of course, different light sources, and we also have a system for the shortwave infrared region, using an in-gas camera for the wavefront sensor. We can work on the 900 to 1700 nanometer as well. And I think it's time for a final Q&A. Jérôme, do you want to go over that and select some? I think there are quite a few questions there. Hello?
yeah, most of the questions have been processed through the app. I'm thinking of like maybe sharing a few of them. Can you measure a convex mirror with this system?
Yeah, yes. Yes, it's possible to measure convex mirror, but the idea is to completely shape the light that is at the output of the R-FLEX 2. For example, you can enlarge the beam and then focus the beam to the F number needed to characterize the concave mirror in autocollimation by focusing the light in the center of curvature of the concave mirror. We don't have standard modules that is dedicated to this application, but if you want, we can try to design a specific one in order to create a converging beam, in order to be able to set the concave mirror in the center of curvature, in order to retrieve the autocollimation thanks to this mirror.
Hi everyone. We want to start a poll of 4 questions, and if you can answer them, that would be great. So our first poll is starting now, and during this time, Jerome or Philip will also be looking at the question and answers and willing to provide answers for your questions.
So there's a question regarding the scaling of what's being displayed. I'm not sure to entirely understand the question, but maybe you will, Guillaume. So let me read it. With the LA 100, can you scale your wavefront to the size of the object? It appears to be the camera scale at the moment.
Yes, this is an interesting question. No, the software does not allow to do that. You're right. The display here we see on the wave view still remain on the wavefront sensor side, which means that we do not take into account the magnification created by the focal system, consists by the modules and the large lens. We discuss a lot about this while we specify the software. In our point of view, it's a best way to allow our customer to do huge error while interpreting the measurement. Because if you allow the customer to change the magnification, you'll be able to interpret the data that is displayed completely wrongly. So it's a choice that we did. The only answer I can do is that extract from the wavefront sensor, from the software, the data file, and do the magnification yourself using your preferred tool, Excel or Python or I don't know.
Okay, I think we're about to conclude this. Let's, I mean, offline, you can definitely contact us, Jerome or myself. Don't hesitate to do that, and we'll relay the questions. We can connect Guillaume with the people, no problem, and we can go from there. I hope everyone appreciated that the event. And again, we have 2 more webinars coming, and we'll send invitations to everyone. Thank you, and have a nice day.
Thank you.
Goodbye, everyone. Thank you.